Right. So this circuit, for instance, guys, would you say that this is a series circuit or a parallel circuit? Do you remember the difference?
Yeah, by both. Let's see, parallel.
Nah,
Parallel.
that's a parallel circuit. So, Nikolai, if you're wondering why it's not both, well, in this circuit, you have the current splitting when it reaches this junction. If there was a resistor over here, then it would have been parallel series, because then the full current would have passed through that resistor. But anytime the current splits, that's a parallel circuit. If there are no instances where the full current passes through a component, it's not a series circuit. Nikolai. Nikolai there?
Yeah.
Alright, so let me just go through series and series and parallel. What we would have covered so far when we started, we'd have covered batteries, and that gives you DC current, meaning that the direction of current never changes. We would have looked at conventional flow of current, electron flow of current. Conventional flow of current is the one we're going to be using most of the times, and that says current goes from positive to negative. We looked at some electrical components. We looked at a resistor. There are two symbols for a resistor, in case you didn't know, the one with the box and the one with the zigzag line. And a resistor, it resists the flow of current. Jadon, I want you to think about a resistor as, okay, so you know as a hose, like whether you say washing the car, right? You know the hose, right?
Yes, sir.
Okay. If you take the hose and you restrict it, like you squeeze it, what would happen to the flow of water?
You'll get less water.
Right, it would restrict the flow of water. That's what resistors do. It is impede the flow of current. And current is just the flow of electrons. That's what it is. Right? Rheostat. A rheostat is a variable resistor, meaning that you can change the resistance. And this is what it looks like. Again, back with the box or the zigzag, but you need to put the arrow to indicate it's a variable resistor. A switch would create a gap in a circuit if you want, or you could close it. When it's in an open configuration, it's called an open circuit. When it's closed, obviously, it's called a closed circuit. In which configuration do you think the circuit will be on, Nikolai? Tell me, Nikolai, in which situation do you think the circuit would turn on? Open or closed circuit?
Closed.
Closed, because if you look at this, right, will the current be able to pass on the other side if it open? Nope. It has to be closed for the current to pass through. Nice. We also look at semiconductor diodes, right? It only allows current to flow in one direction. Jidon, you know about one direction? Or no?
Yes, sir.
Okay, I didn't think I know what I know about one direction. Alright, this is what a semiconductor diode looks like. It sort of looks like an arrow, and that's intentional. So a semiconductor diode only allows current to flow in one direction. When the current is flowing, it's said to be in forward bias. If it's in a configuration where the current is not flowing, it's in reverse bias. Let me explain. Can you all see that the diode sort of looks like it's in this direction? How many of you all seeing that?
Yeah.
Um, Wait one moment. Alright, yeah. So, that direction. So if current was flowing, do you think the diode would allow the current to keep flowing? Yes or no, Nikolai? Alright, so Nikolai, look at the configuration of the diode. The diode looks like it's pointing in this direction. So would it allow current to flow like this?
Yeah, well, I'm trying to play that.
Yeah, but if I reverse the flow of the current, would it be able to pass through the diode?
Stop.
It would stop it. That's why we call it a semi-conductor diode, because semi means half, so it only conducts half the times. If you think about it logically, semi means half. So when the current flows forward bias, when it doesn't flow reverse bias. And this is what a diode looks like in real life. And this is what the IV graph looks like. So it does not conduct. There's no current flowing when the voltage is negative, but when the voltage is positive, it starts to conduct. We also looked at light emitting diodes. Right, we also looked at light emitting diode, and a light emitting diode is also a diode. So if it's also a diode, do you think, guys, anybody here that's mess with electronics? Shana, Nikolai, Jidan, anybody that's mess with electronics? Any of you guys mess with electronics or not?
No.
Nikolai, I feel like you just mess with electronics. Kinda. Alright, Nikolai, you ever take apart a LED and like try to put it on with a battery on a... Does it light all the time, or like do you have to connect it in a certain way for it to light?
That's it.
Exactly. So Jadon, I just tell you is a diode, you know. A diode only allows current to flow in what?
One direction.
Right, in one direction. So you need to look at how you have the LED connected to the battery. You need to look at the polarity, right? So LED is very specific. If you don't have the polarity correct, it's not going to light, because current has to flow through it as per the direction of the diode. So the diode would light here because the current is in the direction of the diode, so forward bias, light LED would come on. But if I try to hook up the LED like this, it would not turn on. So let me give you an example. Right, fast. Shina, what's the symbol over here? Fast, fast, fast. What's that, Shina? What is that? Tell me, Shina, what's that? Sheena, talk to me. I'm not hearing you. Okay, I am not hearing Sheena. Alright, Nikolai, do you know what that symbol is? What it represents?
Yeah, a battery or a cell.
A battery or a cell. This is a battery. Hey, good morning, Ryan. Good morning.
Good morning.
Yeah, boy, I really thought you was doing maths, you know.
Sorry about that.
Yeah, boy. Alright, so in physics, we're looking at the electrical part of physics, right? Did you start this in school or no?
No.
No? Alright, you'll be fine, don't worry. So, Jadon, this is a battery. You know that or no?
No.
Alright, Ryan, did you know that represents a battery?
Yeah.
Alright, and you know it's a battery, right? Like, I mean, it's been your remote and thing. It is.
Yeah.
Alright, Ryan, you into electronics and thing or no?
Yeah.
Alright, do you think a battery gives you direct current or alternating current?
Direct current.
Yeah, direct current, right? And that means that the direction of the current remains the same. It doesn't switch. Alright, so here what? We have a battery here. I'm going to put a resistor. LEDs are sensitive things. Guys, Ryan, you know that LED? LEDs is like last real long, or it might stop working? Or in your experience, LEDs
Yeah, lights.
is lights, right? Light.
Yeah,
Do lights work forever? Do they blow occasionally?
they blow occasionally.
Yeah, Nikolai, Jiran, Shana, that makes sense, right? And at least one point in your life, and you had to change that bulb. I hope. Jiran, you ever changed that bulb before?
Yeah.
Ryan, you ever changed that bulb before?
Yeah,
Okay, so here what? LEDs are very sensitive. So if they get too much current, they go what? If too much current goes
Blow.
out, they go blue, right? Nikolai, Jiran, Shina, they go blue, right? So we typically put a resistor before the LED. And the resistor is there to tell me, Nikolai, what the resistor is there for?
So the black current uses the black current.
I'd not say it's otherwise, it's stop. Because current is still flowing, but it just restricts the rate at which it flows. So it restricts it. Right? It impedes the flow of current. Right? I'm gonna put the diode here. Right, so Ryan, that's the symbol for LED, right? That triangle with the dash and the arrows. The arrows indicating that emitting light. So, Ryan, do you know which terminal is the positive terminal?
no.
Alright, Nikolai, do you know which terminal is the positive terminal?
You take that one.
The longer one is the positive terminal. And if that is the case, Jaden, which one is the negative terminal?
The short one.
The short one, right? Which one do we use? Conventional flow of current or electron flow of current? Nikolai, I think you was there for that class. Conventional or electron flow of current?
Conventional.
Conventional. And conventional flow of current, it goes from positive to negative. So, Jaden, the current is gonna go from the positive to the negative. You with me?
Yeah.
Will the current be able to pass through the diode?
Yeah.
Yeah, Ryan, if you're confused, a diode only allows current to flow in one direction. And again, this is the diode part here. Can you see that the diode sort of looks like an arrow?
Yeah,
Right. The current is in facing that direction, so it's going to let the current pass through. And once the current reaches back to the battery, you have a complete circuit. And so the LED would light up like sketches. I don't know if I get a joke. I never hear light up sketches. I never hear that. Jidon, you know what I'm talking about?
Yeah.
Nicola, you know what I'm talking about or nah?
Yeah.
A long time I hear that. Alright, so I have a question for you all now. So the only thing I'm going to do with this circuit, I'm going to take out the battery and I'm going to flip it around. If I flip around the battery, what will change? Want to know
the flow of current.
the direction of the flow of current? The direction, which is what I think you meant. So remind me, which terminal is the negative one,
Smaller one.
right? And this is the positive one, right? So Jaden, how will the flow of current look like now? Would it still be like this?
No.
No, what happened to it?
It will stop by the diode.
It will stop at diode, right? Because now it's going to flow in this direction. But you see this over here? That come like the border. Right, that come like the border between America and Mexico. Right, that's Trump. Right, so the diode, so the current not going to pass through. Current not going to pass through. So will the LED ever light? Will the LED ever light?
No.
No, it won't light. So in which scenario would I say I'm in forward bias? Scenario 1 or scenario 2? Which one is forward bias?
One.
1. Which one is negative? Which one is reverse bias?
Two.
2, right? Okay, cool. Application of diodes, by the way. Diodes is rectification when you're trying to convert alternating current to direct current, because it is only allow current to flow in one direction. But when you reach that stage, you go see what I mean by that. We also looked at the ammeter and the voltmeter. If you all had to guess, what do you think an ammeter measures?
Ampere.
Amperes, which is a measure of what? As a measure of what? What? Current. Current. Right, so Shayna, you're a little quiet. Shayna, you alright? I'm struggling to hear you. You just what? All I hear is Shayna. I just like like SpongeBob and thing, right? When the people talking on the phone, it's like I just see it like that. I want to know if it's my speakers or something. Like all I hear and Shayna, or no? Like
No.
okay. I don't know what I'm talking about, like in SpongeBob and thing. When the people talking on the phone, it's like it's like a bunch of mumbling. Yeah. Oh, okay, no problem, Shayna. Alright, no problem. Alright, cool. So, Nikolai, Jaden, Ryan, Shayna, an ammeter, it measures current. Now, if we want to measure current, do you think I'll put the ammeter in series or parallel? Okay, wait, before we even do that, I had to explain what is series and parallel, right? Because I don't think I'll know the difference completely. Right, Ryan, you know what is series and parallel?
No.
Jaden, you know what is series and parallel?
No.
Nikolai, you know what is series and parallel? Well, Shayna, Nikolai, you supposed to have an idea, but that's okay if you don't. Nikolai,
Is that what?
you know the difference between series and parallel?
Yeah, series is when current only flowing through one way, and parallel is when it have different ways. So if you cut off one of the series,
Exactly. So, look at this, right, guys? What's the name of that component there again? What's the name of that component? Jaden, did you know that those are two resistors?
yeah.
Ryan, how about you? Yeah? Alright.
Yeah.
Which terminal is the negative terminal? Remind me. Which terminal is the negative one?
Short one.
Smaller one.
And is the positive? So the current go flow from positive to negative like this. I want you to pay attention to the flow of current, right? And I want you to tell me if it's split at any point in time or if it's just flowing in one continuous loop. Did the current ever split?
No.
No. So the same current going through this resistor and it going through this resistor. I hope all you're seeing now, right? It's the same current that flowing right through. So you know what I call this? This is a series circuit. So I'll say it again, Jaden. Why is that a series circuit? And
The current flowing in one direction.
right, so the current never splits. The same current goes through R1 and goes through R2, the resistors. Ryan, I have a question for you. I want you to tell me if this is a series circuit. Tell me, Ryan, there's a series circuit.
Yeah.
I'll try to tie. I really try to tie up all you know. Anybody want to tell me why this is a series circuit?
Because it never split.
It never split. It had to go on an amusement ride. I lot of zigzags, but it never split. Alright, so this is still a series circuit. And of course, alright, I'm putting resistors here, right? But any component in the circuit could be in series. Let me make sure I understand that. So that's with resistors. But any component in a circuit could be in series. So for instance, somebody give my electrical component. Give my electrical component fast.
Ohms?
Ohms is not an electrical component. That's a electric. That's a unit of resistance. That's not a component. Anybody want to tell me a component? You have plenty components in a circuit. Alright. Let me jog your memory. Have all of these components. Give me a component.
LEDs.
LEDs, sure. Sure. Why not? Alright, I want you all to tell me if this is a series circuit or a parallel circuit. What's that?
Series.
Ryan, you agree that that's series?
Yeah.
Why that series? Why is that series?
They're flowing in one direction.
Right, the current's flowing in one direction. But will the LEDs light up?
No,
Why wouldn't it light up?
it won't reach the resistor.
Well,
It won't pass the LEDs. Don't pass the LEDs.
Nico, why wouldn't it pass through the LEDs? Why wouldn't the current pass through the LEDs?
because we can block.
Yeah, again, buck. I say buck. Again, block. It's in reverse bias. I'm telling you, Jadon, when you call me, right? So, okay, Jadon, aren't you a new student? Like this is like the first time you're joining, right? The physics class. Right, you and Ryan.
I join maths.
Right. And I see in March, I was like the first time physics. So here,
Yeah.
since physics class start, it's always been 10 to 12. Always. Always.
Oh,
And so, I on my bed, chilling, check any time, I say I'll get 5 minutes. And then you call and I was like, wait. I had put it for 8. I was like, oh my god. Yeah.
oh,
Yeah. That wouldn't happen again. Alright, that wouldn't happen again. I'll make sure I wake up on the start class on time properly. Alright, so sorry about that, guys. Yeah. So, Ryan, do you understand that this is a series circuit, but the LEDs wouldn't light because it's in reverse bias?
Yeah.
Alright. So I think we understand series, right? One last circuit. Anybody willing to tell me what that component is? Anybody wants to tell me what what that component is? Does anybody know?
Which one?
This one.
Alarm.
Yeah, a lamp or a bulb, right? A lamp or a bulb. Okay, Ryan, you understand that?
Yeah.
Let me be clear, Ryan. A lamp, okay, Ryan, do you think a lamp slash bulb is the same thing as a LED?
No.
No, Nikolai, do you think they're the same thing?
Yeah.
No. Let me show you all the difference. A lot of students think it's the same thing, but no, they are not the same thing. So, Nikolai, you know how a LED kind of picky, and it depends how you hook it up for it to work? And Nikolai, I'm gonna be here, man.
This is it.
Yeah, Nikolai, you know how a LED kind of picky, right? You have to hook it up in a specific way for it to come on.
Yeah.
A bulb not picky. It okay. It will come on. Let me show you all what a LED what a lamp is. Copy image. Alright, this is a lamp. This is a lamp. Oh, you know how alarms work? Or no? You all know. Or nada? If you don't know, that's fine. No, tell me. Tell me, I will explain it. Ryan, you know? Alright.
It does light up.
It is light. Yeah, it is light up. It is light up. But why does it light up? That's the question. Let me explain. Do you know what a short circuit is?
No.
No? Okay. So can everybody see that these are the terminals of the battery, yeah?
Yeah.
If I take the terminals of the battery and I connect them together directly, I create a short circuit and the maximum current would flow and it would get hot. Or you could try it. Actually, that's bad advice to give. I get burned like that when I was small. When I was small, I was really messing around with electronics, but you could test it if you want. You could take a piece of foil and you could connect the both sides of the battery together, and you see that the foil would heat up because a large amount of current will flow through it. But anyways, a bulb works in a similar concept, right? If I hook this up to a battery, let me explain what's gonna happen. So the current is gonna flow. Give me a second. Let me zoom up on this more. It will make a lot of sense, I promise, guys. So let's just say I connect this to the battery, right? Positive, negative. Are you seeing that? Are you seeing that? The flow of current for the bulb.
Yeah.
This is effectively a short circuit, you know, because it's just wire. Right? It comes like you're connecting one side of the battery to the other side directly. And so let me explain what happens. Anytime you short a battery, you're creating large amounts of heat. Why? Because the maximum current flowing. And so you see this wire, isn't it a bit thinner than the others? Isn't this wire here a little thinner than the others? I'm not sure if you're seeing that.
Yeah.
Right. If the wire is thinner, it's going to get heated up faster because you have more collisions between the electrons. Remember, the flow of electrons is current, and so if you have a thinner conductor, it's gonna heat up. And when metal heats up, what happens? Tell me, guys. When you heat up metal, what happens?
Does it get hot?
Nikolai, and when you heat up a metal, it get hot. Right, and that's quote unquote common sense, right? If you heat up a metal, it'll get hot.
Yeah.
When you heat up a metal, real hot, what does it start to do?
Melt.
Yeah, it just melt, but before it melts, well, I want you all to think, tie it into this. This is our what? What is this? What is this? This is our what?
Bulb.
A bulb. What bulb is produced?
Light.
Alright, so when you heat up metal, what's happen?
It become brighter.
Right. Wait, I will show you all a image, right? So over here we have hot metal. What is the hot metal doing? What is got
Glowing.
Nikolai, Sheena, Jaden? What's the hot metal doing?
It's glowing.
And if something glowing, it's producing.
Light.
Right, Nikolai, please let me know if you're seeing that. Like, are you seeing that when you heat up metal, it is at a glow red? It is at a. You seeing now or no? Nikolai? I don't hear Nikolai, but Jaden and Ryan, all they understand that, right? Like when you heat up a metal, it's get hot. And it's at a glow, red.
Yeah.
So that's how a bulb works. You effectively have a short circuit. There's a vacuum over here to prevent the metal here from melting, but that's what it is. So you have a short circuit, and you see this thin piece of wire that gets really really hot because you have a large amount of current flowing through it. That gets really hot, and that is what produces the light. The fact that this metal is getting hot, that produces a light, and a bulb doesn't care about the direction of current. It does not. It does not care about the direction of current. If I reverse the polarity, it's still gonna light up. Can you say the same thing for a LED though? Yes or no? Can you say the same thing for a
No.
LED?
No.
You can't do that. A LED depends on how you hook it up because it's a diode in nature. Anyways, so a lamp and an LED is two different things. I don't know what LEDs look like.
Yeah.
I have trust issues, so let me show you all. Yeah, this is what LEDs look like. Watch it. So it's a completely different structure. So you have the anode, which is the long one. You have the cathode, which is the short one. You have the metal, right? So can you see that, guys? Can you see that that this whole thing is the anode? This whole thing is the anode, and this whole thing here is the cathode. When you look at it, does the anode and cathode, but does the anode and cathode directly touch? Tell me, does it?
No.
I can zoom up a bit more so you can see it.
No, it don't touch.
All right, Nikolai.
No.
Nikolai, you was talking to me, and then you went quiet. You with me or no? I hear Nikolai at all. Nikolai, Shina. Wait, boy. Alright, Jaden and Ryan, it's like the outside churn, you know? Or is the inside churn, I'm supposed to be talking and thing. But anyways, yeah, Jaden and Ryan. Can you all see that you're not touching?
Yeah.
Yeah.
Alright, cool. Let's look at the structure a bit closer. You notice it have a thin piece of wire jumping from here to here. Are you seeing that or no?
Yeah.
Look at it. Jaden, you see any thin piece of wire jumping from the anode to the semiconductor die?
Yeah.
Yeah, this little thing here, this little thing over here, that's the semiconductor die. Now, a semiconductor, okay, a LED, you know what LED really good at? You know what it's really good at? A LED? Take a guess. What do you think a LED is good at?
Light it up.
Exactly, emitting light. So, it'll form a closed circuit and the semiconductor die will emit light. Now, that process is very different from just heating up metal and producing light. Do you all understand there's a difference? One is specialized to make light, and one just happens to make light because the metal getting hot. There's a big difference. But which one do you think is more efficient, Jaden? The LED or the lamp?
The lamp.
No. Let me explain something, right, Jaden? Which one do you think would produce more heat? The LED or the lamp?
The lamp.
If you want, okay, Ryan, what is the main purpose of a lamp or a LED? To do what?
Emit light.
Jaden, do you really want it to emit heat?
Oh. No.
No, so that come like wasting energy, does it not? If it
Yeah.
emits right. So think about it. The LEDs are a lot more efficient because it emits a lot less heat. We don't want it to emit heat, you know. If we wanted to emit heat, we go buy a heater. The point is, we only wanted to emit light. So this is a lot more efficient because LEDs are specialized in emitting light. They are light creating devices. The only reason this producing light is because of what? Why are producing light? Tell me, why are producing light?
Because of the
It
heat.
heats up.
Yeah, because the metal getting hot. And if metal gets hot, it starts to emit light. Cool. So happy that we understand the difference now. But anyways, tell me, this circuit is a parallel circuit or a series circuit? Okay, tell me. Series or parallel circuit?
Series.
Yeah, series. So all the components are in series, right? Every single component there is in series. Now, you notice that the current is passing through the what? What device there measures current? I want you all to tell me. What
Ammeter.
ammeter? The ammeter measures current. And so, if I want the ammeter to measure current, does it make sense for the current to pass through the ammeter?
Yeah.
Yeah, that makes sense, Ryan. If you want to measure current, and you would want to see the current that passing through, you would need to see it to measure it.
Yeah.
Right. And this makes sense. Because, okay, do you all know the proper definition for current? Do you all know the definition for current? The proper definition?
No.
Alright. Okay, current is the rate at which charge passes by a point on the circuit in 1 second. So it's the amount of charge passing through the circuit between 2 points in 1 second. So the ammeter is going to measure the amount of charge passing through passing through it in 1 second. That's what it's going to do. So you would need the current to pass through the ammeter so you could measure the rate at which charge is passing through the ammeter. You need the current to pass through the ammeter for you to measure current. So in that sense, we always hook up an ammeter in what? For you to measure current, you need to hook up an ammeter in what?
Series.
You need to hook up an ammeter in series. Why? Because the current needs to?
Flow.
It needs to flow through the ammeter. Alright, let's look at parallel circuits now. So we should be okay with series circuits. Before I move on, you need to know how to combine resistors in series. It's really simple. Ryan, if you want to combine resistors that are in series, you literally just add them. That's all you're gonna do. You're just gonna add them. R1 plus R2. Doesn't get easier. If you had a third one, what do you think you'd do, Ryan?
Add that one too.
That's all. That's literally it. That is literally it, right? That's all. Now, if you have a series circuit, there's only one path for current to flow. That's the first thing. If one component fails, this creates an open circuit. Let me explain. Alright. Ryan, if this resistor burns, what happen?
They only have one more resistor.
Right, but it have a big gap in the circuit. Have a big gap in the circuit now. You think the current
Yeah.
to jump from here to here now?
No.
No, it have a big gap in the circuit. How we gonna do that? It come like you're driving on the road and the bridge break down. How you gonna pass? Can't pass, right?
No.
No, Jadon. Nikolai. Wait, let me talk loud. Nikolai, you hearing me? No rain falling. Nikolai, you hearing me? Hey, boy. Hey, trying to talk loud. Call Nikolai. Give me a second. Yeah, Nikolai here, no? Nikolai here, no? Alright, well, let me do that then. I gotta make sure you understand this thing. I gotta make sure you understand it. Alright, so I'm saying that if one resistor blows, the whole circuit gonna fail. You understand why?
Yeah, because one go current don't play properly.
Right, it wouldn't be able to flow, right? Because it'd have a big gap in the circuit. Alright, let me move on. And something to understand, guys, the current through each component would be the same. I'm not sure if you'll understand what I mean by that. The last one, I'm saying the current through each component is the same. Can you all see that the same current going through this one and the same current going through this one? Right, let me know if you're seeing that. The same current passing through both of them.
Yeah.
Alright, cool. Let's look at parallel now. Right. What would happen over here? Somebody tell me what would happen over there. What's gonna happen at that junction?
It would split.
It would split. Nikolai, you understand that? It would split.
Yes.
So tell me, Nikolai, would the same current go through R1 and R2, or like a different amount of current?
Different amount.
Right, a different amount. Good. Jadon, do you understand that at this junction the current is splitting?
Yeah.
Right, because there are two paths to take. Anytime there's more than one path to take, it's a parallel circuit you're dealing with. So the different currents are going to go through R1 and R2, but eventually they're going to meet back at this point, and what's going to happen here?
It will continue to flow.
Exactly. Now let me explain something, Ryan. In terms of the circuit, this is the total current, or like some portion of the total current, if you were to say.
A portion of it.
Nah, that's the total current. That's the total current. Let me ask you a question, Ryan. Did it split yet? Did it split yet?
So
No, it didn't split yet. It only splits at this point. So I'll ask the question again. This is the full amount of current or a portion of the current?
the full amount.
Yeah, that's the full amount of current. The full amount of current. But over here, it what? What is what happens to it?
Split. So it would be a portion of the amount of current.
Right. And when the current meet back at this junction, it gives you back what?
The total amount of current.
Yes. That's it. If you all go to pursue physics at a higher level, you'll learn about Kirchhoff's current law. Right? It says that the sum of currents entering a node is equal to the sum of currents leaving a node, which is similar to this. So you have these currents entering this node, and you have this current leaving the node. So they must add up. They must add up. I hope that makes sense, right? If the two currents merging together until give you back the total current.
Yeah.
Yeah, okay. Nikolai, this question is for you. I want you to tell me, this is a series circuit or a parallel circuit? Tell me, Nikolai, what is this?
It look like a parallel.
Wait, Nikolai, you talk on Zoom? Okay, I swear here, Nikolai. Yeah, say that again, Nikolai.
Yeah, the insert is outside, you know better now.
Oh, okay, cool. Well, I will hang up on WhatsApp then. Yeah. So, Nikolai, what is it looking like?
A parallel.
Just a parallel?
A series for mostly parallel.
Mostly parallel. Let me examine this. Let's examine this. So the current is gonna leave the positive. What's gonna happen to the current at that junction or node?
And split.
It's gonna split. What do you noticing over here? Even though it's split, what are you noticing?
Or it have more than one resistor.
Right, but these two resistors are in what? What are these two resistors in?
Series.
Jiran, Ryan, Shina, can you all see that those resistors on top, the two on top,
Yeah.
they are in series?
Yeah.
Right. So this is actually a case where we have a series and a parallel. So these two resistors on top are what together? Are what? They are what?
Series.
And
Series.
these two resistors and this, they are what together? They are what?
Series parallel.
Parallel. If you wanted, you could have combined these two resistors into one. Right? If I told you that this was 100 ohms and this was 50 ohms, what would the combined resistance be? Tell me, Ryan.
150.
150, because if you have resistors in series, you just add them. So I would have a 150 ohm there, and let me just say we have a 70 ohm here. These resistors will be in what?
Parallel.
Exactly, parallel. Cool. So I feel like we understand the concept. Now I need to talk about voltage, right? Do you all understand that a battery has voltage?
Yeah.
Right. Now, how much terminals it have in a battery? Think about it, guys. Shana, Nikolai, Jaden, battery. How much terminals a battery have? Two.
Two.
So, what voltage really is? Voltage is actually the difference. Is actually the potential difference between 2 points. That's what it is. That's why for a battery you need two poles. I'll say it again, Ryan. Ryan, you know his potential energy or no?
Yeah.
Alright. So the higher you are, we're gonna increase.
Potential energy.
Right. Jaden, Nikolai, do you all, well, I don't know I did energy with my students, but Jaden, do you know about potential energy?
Yeah.
Nikolai, do you know about potential energy?
Yeah, I believe so.
Alright, so you know what's the formula for potential energy? And Nikolai? Potential energy formula for that.
Nah, I remember.
Alright.
BH.
Mass by gravity by height, right? Mass by gravity by height. So as the height increases, what happens to the potential energy?
It increases.
Alright, the potential energy increases, right? So Nikolai, the further you climb, okay, I'm not insinuating anything, but Nikolai, let me just say you climb up a 1-story building and you're at the top. If you were to jump, would it be catastrophic?
No.
Okay, if you go up a 5-story building and you jump, would that be catastrophic?
Maybe in early wall.
Say that again?
Maybe in early wall. That's a structure just no.
Wait, boy, this man in Ninja Warriors. This man say he'll be fine if you jump from a 5-story building. That's crazy. Okay. What about a 100-story building? You go survive that one, Nikolai?
No.
Nah. So the higher you go, it becomes deadlier, right? But why? That's because the potential energy goes up. Right? The potential energy goes up. So when you jump, that energy is gonna be converted to kinetic energy, and you're gonna experience a greater force when you hit the ground. Again, I'm not insinuating anything, but I just use an example. A bit of a morbid example, but Nicola, again, I'm not insinuating anything. But long story short, the higher you go from the ground, what increases?
The potential level. Potential energy.
Right, a battery is similar. Right, we're looking at the potential difference. The difference in potential between the two terminals. So you see this negative terminal, you could consider that 0 volts. Maybe that could be 0 volts. And this positive terminal could be 5 volts. What's the potential difference? What's the difference? What's the difference?
5 volts on one side and 5 volts more.
Well, the difference between 5 and 0 is what? What's the difference between 5 and 0? Somebody tell me. 5 and 0.
I haven't had any X1.
What is it?
5 is more than 0.
No, like difference, like subtract. So 5 minus 0 is what? What's 5 minus 0?
5.
5. Cool. So the potential difference across these terminals is 5. So you'll see they write 5 volts on the battery, right? 5 volts on the battery. That's what potential difference is. So potential difference is the difference in potential between 2 points. That's what it is. That's why a battery has 2 terminals, because it's the difference across 2 points. So if you want to measure voltage, you need to measure the difference across how much points. Tell me, Ryan, if you want to measure voltage, you need to measure the difference across how much points?
4 points.
2 points. 2 points, right? Again, potential difference. You would find the difference between what? Like if you had to find the difference, what you do? Like if I tell you 9 and 7, what you do? To find difference.
Subtract it.
Right, so you find difference between two terms. So if you want to find the voltage or the potential difference, you're gonna measure the difference between how much points?
2 points.
2 points. Good. 2 points. 2 points. So that brings me on to the other thing. A voltmeter. A voltmeter measures voltage. Or in other words, potential difference. Voltage and potential difference means the same thing. So okay, so you see how we're going to hook up our ammeter in series? You see how we're going to hook up our ammeter in series because the current has to flow through it? I'll remember that?
Yeah.
Or you don't figure that? Tell me. Remember that? The ammeter in series, so current could flow through it.
Yeah.
Alright. Well, again, we measure voltage by measuring the difference between 2 points. Difference between 2 points. So I actually have to hook up a voltmeter in parallel, and you'll see why. So across, let me explain this, right? So Ryan, every electrical component that I put in the circuit, it's going to consume, well, there's going to be a voltage drop across it, right? Think of it like that. So across this resistor, some voltage will drop. Across this component, some voltage will drop. The point is, every circuit, okay, every component in the circuit has a voltage drop across it. So we need to measure the difference between 2 points. So Ryan, remember what I tell you, voltage is potential difference and is the difference between 2 points in our circuit. So can everybody see that we have a resistor over here? Yeah or no?
Yeah.
Right, if I want to measure the voltage across the resistor, I'm going to take my voltmeter and I'm going to put it over here before the resistor, and then I'm going to place it after the resistor. And I'm doing this because I want to measure the watt between these 2 points. Remind, somebody say the word. I want to measure the what?
Difference.
Not just difference, the what? I want to hear the full thing. Nikolai, Jiran, Zachary, you all have the potential.
The potential difference.
Right. I'll give all a little hint on thing here and there, you know. I literally give it to Ollie just now. I say Ollie had the potential, right? So yeah. Ryan, potential difference. So anytime you're measuring voltage, it's across a component. So you need to hook up the device in parallel. Can you all see that I have the voltmeter here in parallel to the resistor or no?
Yeah.
Well, let's see now, right? Because the current here would quote unquote split. Cool. if I wanted to measure the voltage across the diode, I would do the same procedure. I would measure before the diode and after the diode, because across each component in the circuit you have a voltage what? A voltage what? A voltage what?
A voltage drop, sir.
A voltage drop, yes. Right? So Jadon, just to make sure you understand, each component in the circuit is going to experience a voltage drop. So some voltage is going to be dropped across the components in the circuit. Understand that?
Yeah.
Right. So it come like, let me explain. It come like energy, right? The component's gonna use up the energy, if you understand what I'm saying. And so would all the components use up the same amount of energy, or some would use a different amount of energy?
Some with different amount of energy.
Right. So think about this as the maximum potential, and across the components, different components would use different amounts of that voltage. Some might use 5 volts, some might use 8 volts. But here's the thing, guys. If this is 12 volts, right? If that is 12 volts, I only have 12 volts to work with. Only. So you know what? Maybe it might have 3 volts across that. And if it had 3 volts across that, how much volts do you think it will have across the resistor then? For that to say.
9.
9. Right? 9. It have 9 volts across the resistor. Now, if you're telling me, sir, but you're kinda skimping over this ammeter. Let me explain something, right? The ammeter, what's the only reason I have the ammeter in the circuit there for? What's the only reason I have it?
To measure current.
Do I want the ammeter to do anything else than measure current?
No.
Zachary, Nikolai, Jiran, Shina, do I want that ammeter to do anything else?
No.
Oh, sir.
No. So the only purpose of ammeter is there is to measure current. I don't want it to mess with the circuit in any way. I don't want it to even do anything. So I have a question. Do you think the ammeter will use up any voltage?
No, sir.
No, because Ryan, the ammeter not supposed to do anything. It's just supposed to measure current. Right, Ryan? So
Yes, sir.
when you put a ammeter or a voltmeter in a circuit, it's not supposed to affect the properties of the circuit. So let me make sure I understand this. The ammeter, you hook up an ammeter in the circuit. How would you hook up an ammeter to measure current?
Series.
Right, Ryan, Jaden, Nikolai, Shina, all you understand that, right? You hook up an ammeter in
Yeah. Series.
series. Do you want the ammeter to affect the properties of the circuit?
No.
No, you don't want that. You do not want that. So do you think the ammeter should have a high resistance or a low resistance?
Low resistance.
A low resistance, Ryan. You think you can tell me why we want the ammeter to have a low resistance?
Because we don't want it to affect the circuit.
Exactly. If it had a high resistance and it would have restrictive flow of current.
Yeah.
Right. Now let me explain something to you all. Do you all know about V is equal to IR?
Yes, sir.
Okay. Here's something, guys. If the component has a high resistance, the voltage across it will be subsequently larger because V is equal to the product of current times resistance. The greater the resistance, the greater the...
Voltage.
Right, so Ryan, stay with me, right? Ryan, if the ammeter has a resistance of 0, what would the voltage be across it? 0, because we don't know what the current is, right? But if you know R is 0, anything by 0 is what?
0.
Exactly. So Nikolai, if I lose on you, just tell me, right? Nikolai, talk to me.
No, sir.
Alright, so Nikolai, here I saying again, Nikolai, do I want the ammeter to affect the circuit? Yeah or no?
No.
No, I don't want the ammeter to affect the circuit. So should the ammeter have a high resistance or a low resistance?
A low resistance.
Right, because if it have a low resistance, what would the voltage drop be across it?
0.
0, because of Ohm's law, V is equal to IR. voltage is equal to the product of current flowing through the component by the resistance. Right, we don't know what the current is, but Nikolai, if we know the resistance of the ammeter is 0, what's I by 0?
0.
Exactly. And question, if 0 volts is being dropped across the ammeter, is it affecting the circuit or is it not affecting the circuit?
I'm not affecting this circuit.
Right, because it come like the ammeter not using up any energy in the circuit, right? That's what it come like. It come like the other components are going to use up that energy, which is what we want. We don't want the ammeter to do anything. That ammeter should not be doing anything. So, long story short, when you are using an ammeter, it needs to be connected in what?
A series.
It needs to be connected in series, not a series. It needs to be connected in series. And should it have a high resistance or a low resistance?
Resistance.
Low resistance. Everybody okay with that?
Yes, sir.
Yes, sir.
What does an ammeter measure?
Current.
Current. And what is the unit for current?
Amps. Amperes.
Amperes, right? Cool. Let's move on to the voltmeter now. So remind me, the voltmeter measures the... What does the voltmeter measure?
Voltage.
Voltage, or you could say what?
Potential difference.
Right, which should be the difference across how much points?
2 points.
I hear 3 points. Is it 3 points or 2 points?
2 points, sir.
2 points. 2 points. So would I connect a voltmeter in series or parallel?
Parallel.
Right, because Ryan, when you connect something in parallel, it's across how much points?
Points.
2 points. Good. So Nikolai, I want you to help me with this part, right? So Nikolai, when the current reach this junction over here, what happen?
Will continue flowing. The current goes along.
It will continue flowing, but what will it do?
It will split somewhat, because it will go into the volt and resistor.
It will split. Let me ask that question, Nikolai. Do you want the voltmeter using any current in the circuit? Do you want it to mess with anything?
Yeah.
Nah, I don't want a voltmeter to mess with anything. The only thing I want a voltmeter do is measure voltage and mind the business. I don't want a voltmeter doing anything else. So, Nikolai, do you want current to pass through the voltmeter?
Nah.
No. Does the voltmeter measure current?
Yeah. No, nah.
Nah. Jadon, does the voltmeter measure current?
No.
No. So, if it don't measure current, we want current to pass through it?
No.
No, Nikolai, we don't. So, Nikolai, what would you put... Okay, what would you want if you don't want current to pass through? You don't want current to pass through, so what you gonna want?
Something to block the current from going through.
Right, so what blocks current from going through?
A diode.
Nah, we need a diode. What's that R?
Or a resistor.
A low resistor or high resistor?
Hello? A high one?
Okay, why is it low? If it's a low resistor, would it block the flow current or would it let current pass through easily?
It will let current pass through easily.
Do you want current to pass through the voltmeter?
So why they go to a high one?
A high one. If you have a high resistor, it's going to resist the flow of current. So only a little bit of current will pass through the voltmeter. In a perfect world, it's supposed to have an infinite resistance. Right? So no current will have passed through, but in real life, it will just use a very high resistance. So I run through it again. A voltmeter is connected in what? How is a voltmeter connected in?
Parallel.
And we want it to have a high resistance or a low resistance?
High resistance.
Ryan, Zachary, Jadon, Shane, are we okay?
Yes, sir.
Right.
Yeah.
Because Ryan, if this have a really high resistance, will a lot of current want to pass through it, or will most of the current pass through the resistor?
So the current will pass through the resistor.
Exactly, because people will say current takes the path of least resistance. That's like an oversimplification, but we could think about it here. Right? Most of the current is going to pass through the resistor because it has least resistance. Alright, cool. So a voltmeter, very high resistance. So let's just do a recap before we move on. What did we look at so far? Well, you guys should know what a battery is now. All you know is a battery?
Yes, sir.
Alright, this is a battery. A battery does produce alternating current or direct current? How fast? It's a pop quiz right now. Alternating.
Direct current.
Direct.
Right? Direct current. Cool. What's the name of this device?
A switch.
Close switch.
A switch, right? And this is a closed switch right now. What about this?
A open switch.
Open switch. What's the name of this component?
Resistor.
Resistor.
How about this one?
Resistor.
How about this one?
Variable resistor.
Resistor.
A rheostat, a potentiometer, a variable resistor. Anyone is fine. Alright? What do you call this component?
Ammeter.
Right. Ryan, tell me, how will you connect this in a circuit? How do you connect an ammeter in a circuit? Putting Ryan on the spot, boy. Ryan, remind me, how do you connect an ammeter in a circuit? And wait, okay, first of all, Ryan, what does it measure?
Current.
Right. So how am I going to connect it? Series or parallel?
Oh. Series.
And it should have a what? High resistance or low resistance? Say that again?
Resistance.
What resistance?
Resistance.
I just saying resistance. High resistance or low resistance?
No resistance.
You're saying low resistance? Why are you saying low resistance? Explain yourself. I want to understand.
Pass through.
Right, you want a low resistance, so you go past through the ammeter. Yeah. Right? Low resistance. Alright, cool. What's the name of this component? Hello, speed.
Voltmeter.
Voltmeter. I hook up a voltmeter and what?
Parallel.
What does it measure?
Voltage.
Voltage. I could also say what?
Yes.
Potential difference.
Right. Potential difference. Our Ryan, I'm gonna call you again. Ryan, high resistance or low resistance?
High resistance.
High resistance, because we don't want any current to pass through the voltmeter. Remember, a voltmeter does be hooked up in parallel, so the current go on to split. You don't want the current to split though, so you want to use a high resistor to prevent the current from flowing through the air. You want most of the current to flow through the resistor, or whatever component it is. Cool. What's the name of this component?
Diode.
Semiconductor diode, right? What do you call this configuration?
Forward bias.
What configuration do you call this?
Reverse bias.
Reverse bias. Right? Semiconductor diode. Where do you use semiconductor diodes? I think you're going to know this one, a rectification. And rectification is when they convert in what to what? Do any of you guys know?
That's
Alright, AC to DC. Do you know what AC stands for?
alternating current.
Right. So you use a semiconductor diode when you convert in AC to DC. Remember that. AC to DC. And you guys will learn about full wave rectification. Which is this? All right, let's keep it moving. What do you call this component?
LED,
Light emitting diode.
All right, what do you call this component?
lamp,
Are they the same thing?
No.
I didn't hear Jadon or Ryan. Jadon, Ryan, is it the same thing?
No.
No.
No, it's not the same thing. Which one is more efficient? The lamp or the LED?
The
The
LED.
LED.
Right, because this actually produces a lot of what? What does the lamp produce? A lot of heat.
Heat.
Right, we don't want it to produce heat. That wasted energy. Nice. Would the LED turn on in this configuration?
Yeah.
Yeah, it would. Would it turn on in this configuration?
No.
No, it wouldn't. Because a semiconductor, okay, a LED has the same properties of a semiconductor diode because it's still a diode, right? It's still a diode. So it only turn on in one specific configuration. What else I need to go over? All right, cool. This circuit over here, series or parallel?
Is
Everybody okay with that, right? I'll just see the current split anywhere.
also
nope,
No, so if I tell you that this was 5 ohms and this was 7 ohms, was the combined resistance RT?
12 ohms.
Right. Ryan, you okay with that? If you have resistors in parallel, you just add them.
Yes, sir.
Alright, cool. What if I had... Alright, so that brings me to this other point. I didn't show you all how to add resistors that are in parallel. So let me show you all how to do that now. So in a parallel circuit, obviously you have multiple routes current can flow. So let me explain something. If you was driving and you have 3 different routes you could take. Let me just say it have a log, a tree furlong, right? And you over here. If a tree fall along on this road, what you do?
Take another road.
Right? If a tree fall along on this road, what you do?
Take another road.
Right. So in a parallel circuit, it's similar. You have multiple paths to take. So if one component stops working, will the whole circuit stop working?
No.
No, because you have more than one path for current to take. Cool. So in a parallel circuit, there are multiple routes current can flow. Current splits at junctions. The voltage across each component is the same. So this might be one that kind of hard for you all to understand. Let me explain something. Do you all think your house is hooked up in series or parallel? Follow hard to guess. Your house. Parallel. And let me understand why that makes sense. Ryan, if one bulb blow in your house, does everything in the house stop working?
No.
No, everything still works. So it's connected in parallel. Right? So domestic applications use a parallel configuration. Now, Jadon, I guess you never really, okay, no, it's a multimeter.
Yeah, no.
It was moving like alternating current day, boy. It was like, yeah, no. Yeah. That's how alternating current does behave. Can't make up your mind. Alright. That's okay. That's okay. So, Jadon, do you think your fridge or your phone charger or the bulb, do you think they get different voltages, or do you think they are connected to the same voltage?
Different voltages.
Nah, same voltage. Same voltage. Yeah. Same voltage. Same 120 volts. Now inside the devices you have step up or step down procedures. You have step down, or step up circuits. So let me just say a phone charger, right? Do you think your phone charger it sends 120 volts to your phone?
Yeah.
No, no. No, your phone charger, it actually steps down the 120 volts into like around 9 volts, 5 to 9 volts DC, and it sends it to your phone. So here I was saying, right, Jadon, all devices in your house, most of them, they are connected directly to the main socket, and the main socket provides 120 volts AC. That's what it does. So you see the plug in your house? Ryan, Zachary, Nikolai, Shina. You see that plug in your house? That's gonna give you 120 volts AC. AC. Right? And alternating current means that the current is gonna switch direction periodically. They're gonna go from positive to negative, positive to negative, positive to negative, that kind of thing. But anyways, Nikolai, what I'm trying to say, right, Nikolai, all the outlets in your house is 120 volts AC. You understand?
Yes.
Do you think your phone go and use 120 volts AC?
Nope.
No, so that's why you have a wall. That's why you have the brick. And so you just plug the brick into the socket,
Yeah.
the adapter, whatever you want to call it. The brick. Are you not talking about
Yeah, the
Yeah.
block.
the block? The block, yes. That block has components on it inside. Okay, the block has a circuit on the inside. Has a circuit. In the circuit, you're gonna find transformers. You're gonna find resistors. You're gonna find diodes. All of these components, and you're gonna do some magic, and you're gonna take that 120 volts. You're gonna drop it down to like 5 or 9 volts and send it to your phone. Okay. Do you think your fridge can use the same voltage as your phone? Yeah or no? Do you think your fridge would use the same voltage as your phone? I promise it's not a trick question. Ryan, do you think your fridge can use the same voltage as your phone to run?
No.
Your phone is use like 5 to 9 volts, eh? The fridge might actually use the 120 volts AC. But the point is that wall socket. Are you know what I'm talking about? Like on the wall, it have like two rectangular slots. Are you know what I'm talking about? And then occasionally you would have this one.
Yeah.
Yes, sir.
What I'm saying is, if you take a multimeter and you stick it in the wall, everywhere you go, it's going to be 120 volts AC. So in a parallel circuit, the voltage across each component is the exact same. I'll say it again. The voltage across each component is the same. So let me give you an example. Question, guys. What components here are in parallel together? Which components here are in parallel?
Yes, sir.
The resistors. So what do you think the voltage across R1 and R2 would be?
The
The
same.
same?
The same, because these components are in parallel. And furthermore, voltage is potential difference. We could see that both of them sharing the same potential difference. Watch. Both of them have the same potential difference because why? Because both of them between these 2 points. Both of them between those 2 points, R1 and R2, both of them between those 2 points. If I add another resistor over here, that resistor there would be in what? Series or parallel? Tell me fast, guys. Series or parallel?
Parallel.
Parallel, because current split in 3 ways, right? I could call this R3. Would the voltage across R3 be any different, or would it be the same as R1 and R2?
The same as R1 and R2.
Right, because again, it's between these 2 points. That's never changing. So understand this. In a parallel circuit, you have multiple routes current could flow. The current would split at the junction. The voltage across each component is the same. And if one component fails, the whole circuit doesn't break, right? Because there are multiple routes current could take. Are you understand? Or no?
Yeah.
Yes, sir.
Yes, sir.
Yes, sir.
So if I measure the voltage across R1, I take a voltmeter, I put it here. And then I take a voltmeter and I put it by R2. Would I get different readings or the same reading?
The same reading.
Get the same reading. Alright. So I only know how to combine resistors in series, but how do you combine resistors in parallel? Well, let me show you. So either you do this and then you reciprocate, or you just do this, which I recommend. I recommend doing this. This is like the easier way, far easier way. Do you all have Sharp calculators or Casio calculators?
Casio.
Good. Casio is the way to go, right? If you have a Sharp, hard luck today. But I will still show you how to work it. Alright, so let me give you an example. And let's just say we have 10 ohms over here, and we have 5 ohms over here. Cool. If I wanted to combine these resistors, so I wanted to find the total resistance, I would say 1 over 10 plus 1 over 5 to the power negative 1. Now, when you do it in school, you mightn't learn it like this. You might learn it like 1 over RT is equal to 1 over 10 plus 1 over 5. Then you would have to add this and then reciprocate it, but I'm showing you something much simpler. This is real easy. So here's what to do. In the calculator, I want you to plug this in and tell me what you're getting. I want to see if you all know how to use a calculator. So plug that in and let me know what you're getting. If you don't know how to plug it in, just tell me, I'll show you.
3.3.
And I get into the 3.3. Somebody else, but that was a close answer. But Shayna, Nikolai, Jaden, Ryan, plug that into the calculator and let me know what y'all are getting. I'm taking it all. You guys having trouble with the calculator? Shayna, you having some trouble with the calculator? Okay, and I'm not hearing much people. I guess y'all having trouble with calculator. Right? Nikolai, you have a Sharp or Casio? Nikolai, Sharp or Casio?
Neither.
You don't have a calculator?
Nah, the Oxford one.
You can point a camera and show me what the Oxford one does look like. Okay, that don't look too bad. Same thing like the Sharp. That's the same thing like the Sharp. Alright, so let me show you how we're going to calculate this. Because I've seen plenty of things going wrong with all of like with the calculator now. Like, everybody have different calculators. And so, it would cause some conflict there. So let me see how I could help you all with the calculator part. Let me see how I could do that. Okay, so Nikolai, I guess you didn't get through with this part, with this over here. Talk to me, Nikolai.
I reach everything until the negative 1.
Alright. Noted. Jaden, did you get through or no?
Oh, Baba Sharp.
Alright. Ryan, what about you? You get through or not?
I get 3 and a third.
Yeah, 3.33 ohms. That's the answer. That's the answer I want. Zachary, you said to the 3.3, but I think you're supposed to say 3.3.
Oops, I didn't say to the 3.3 yet.
I could have swear you said to the 3.3.
Nah, sir.
Okay, that's why you say that. Alright, so let me show you guys with a sharp how to work this. If I help it, I ban sharp. Ban that. But you use a Casio. Casio will make your life so much easier. Right, so people with the sharp, right? So what you to do? In the calculator, right? So stay with me. You're gonna open a bracket. You're gonna open another bracket. You're gonna press 1. You're gonna press divided by 10. Close bracket. Then plus. Okay, so here what? Anytime you put in a fraction into a sharp, right? Anytime you're doing that, you need to put brackets. So now we're gonna put 1 over 5. So I open bracket, I put 1, I press divided, I press 5, I close the bracket. Right? Then I close the bracket. So I want to make sure everybody is with me. So do you all understand that anytime you put in a fraction, you have to open a bracket, 1 divided by 10, close the bracket. Right? Anytime you put in a fraction in a sharp, that's what you have to do. Let me know. So Nikolai, Jaden, do you all have this calculator so far?
Yeah.
Alright, so what you all are looking for, you're looking for the Y to the X button. Let me know if you all seen that. Y to the X button.
Yeah.
You're gonna press that. When you press that, you should see like this thing pop up.
Yeah.
Nikolai, I'm not hearing you. Your calculator a little different.
Yeah, different.
You have the Y to the X button.
Nah, back time I see that a negative one.
Okay, press that. Alright, so here we're gonna do for Magellan. You're gonna press Y to the X and a little thing like this should pop up. When that pops up, you're gonna open a bracket, put -1, close the bracket.
Yeah.
Right, so you press that to the power -1 and you get 10 over 3, which is 3.33. You get through? Let me know. If you didn't get through, Jaden, that's fine. I'll go over it with you. But let me know. Jaden, you get through or no? I'm not hearing Jaden. Nikolai, you get through or no?
Nah, my calculator give me 5.1.
I get error 1.
Alright, here what? Nikolai and Jaden send me a picture of all the calculator and when you plug in, and I will help you all accordingly.
Yeah, no, I get.
Alright, send me a picture so I can confirm. Jaden, send me a picture. I want to see what's happening.
Yeah.
Yeah, so in the meantime, for those of you all that got through, I want to give you all another question. You all could attempt it.
It don't show the full thing.
Let me see. But Nikolai, look at right there. So let me explain, right? So Nikolai, you see right next to the x squared button, you have this little thing over here. You have this.
Oh,
You could press that and then put in brackets -1. But I see you have the x to the -1 there. You have x to the -1. What you do? You press that?
yeah, press that.
Yeah, that's not a problem, man. You get through one time.
When I do it in the fraction, which then I get 3 and 1/3.
3 and 1/3 is correct. Alright, so Jada, let me see what going on there. Jidan, could I see the start of it, like where you plug in at the start?
Yeah, just now.
Or here what, Jidan, I think I know the mistake. In the sharp calculator, if you press, let me explain something, right? So Jidan, if you press this minus button,
Yeah.
it will say error, right? You actually have to press this one.
Oh,
The sharp calculator is so stupid. Like, it's so stupid. Like, the sharp calculator is so, oh my god. Ryan, you're probably like so happy you don't have a sharp. All of that craziness you had to do with brackets and. So try it back, DJ done. And instead of pressing this negative, press this negative.
I get negative 0.3.
Negative 0.3. Nah. Alright, so let me start back from scratch, right? Right, Jadon. So I want wait to try something else this time. This should work better, I think. So open bracket. So here what Jadon. You see how we have our open and our closed bracket here on either side?
Yeah.
Better start with that. So I press our open bracket. And now you have to open a bracket because you have a fraction here. So I open a bracket. I put 1 divided by 10 and I close the bracket. So I just put in the fraction. Then I'm gonna press plus and I'm gonna do the same thing for the 1/5. So 1 divided by 5, close bracket, and then I have to close the bracket. Good, let me know if you're with me up to this point.
Yeah.
What I wanted to try instead of doing that, what way to try, a way to press second function, pi. Try doing that for me. Second function, pi. Or your calculator a bit different. Okay, what you gotta do instead, right? Right, Jadon, you gotta press second function x squared. Press second function x squared.
Yeah.
Let me get your calculator real quick. Press
I
E.
get 3.33.
Okay, cool. Yeah, that's what you're supposed to get, right? Just confirming, everybody get the correct answer or no?
I feel I invested in a Casio.
Yeah, you had to invest in a Casio, like, because look at this. On the Casio, watch this, right? Open bracket, fraction button, 1/10. Right, cool. Plus, fraction button, 1/5. Close bracket, to the power -1. Bam. S to D. You don't know brackets and thing? I don't hot my head about brackets or how it looking. Alright, so I want to make sure you all could handle this by yourself. So let me give you all a question to do. Alright, guys, those two resistors in series or parallel?
Parallel.
Right, so this is 7 ohms and this is 14 ohms. I want you all to find the combined resistance. So I want you to find the total resistance, RT. Do that for me. I want you to find RT, which is the total resistance.
I get 4.67.
Sick. What? Whoa, whoa, whoa. Say them last two digits.
Yes, it's 67.
Big boy. Jadon disappear.
So the physics classes verification starts at 8 o'clock.
Yeah, boy. Yeah. Yeah. Yeah,
Right.
yeah, this is exactly. I sleep and you know, like how you go wake up, you go look at the time, say, I'll take out 5 minutes, you snooze again, you know.
Yeah.
Yeah, I will doing that. Then I see Jadon calling, and I was like, wait, I'll schedule it for 8 o'clock. I was like, oh shucks, wait, I get up one,
Side,
I get up one time, I get up stupid. I was like, oh my god, let me start class, let me start class. Yeah,
side new. I wake up, it's like 9:20 something. I thought I had enough time to go and brush my teeth and think, but I check the chat and I see class start. So
yeah, boy. Okay, Nikolai, Ryan, Shayna, I'm not hearing from you guys. I give you also a bit of time. Ryan, you get an answer or no?
4 and 2/3.
Say that again?
I get 4 and 2/3.
Alright, tell me the answer to the two decimal places.
4.67.
Right? Nikolai, did you get through or no?
I have 4.6.
4.67, right?
Yeah.
The calculator saying 4.67?
The 7 real far down, but it's in 4.66. And then
Right.
the 7 real far down.
Right. Also, way to in physics, we typically round things off to two decimal places or three significant figures. So I stick in with two decimal places, right? So, Nikolai, if you're seeing 4.666, etc., the second decimal place is 6, the number after 6 is 6, so you're gonna add 1 to the 6, so 4.67. Understand?
Yes, sir.
Now here what? If you wanted, instead of drawing the circuit like that, you could have drawn the circuit like this. So in here what I'm saying, right? Instead of putting two resistors, what I could put? Somebody tell me. Instead of drawing two resistors, what I could do?
Put the combined resistance on the one resistor.
Exactly. So that would be the combined resistance. And what's the combined resistance?
4.67.
Right. So Ryan, do you understand that we could take this diagram and simplify it by combining the resistors?
Yes, sir.
All right. So let me spruce things up a bit now. So I'm gonna end class just now, but in the next class, we're going to deal with some more complex circuits. I'm going to introduce V is equal to IR into the questions, and we're gonna do some past paper questions on this topic. So in this diagram, how much resistors we have in series? Well, I mean parallel.
3.
Do you all know how you would combine these resistors or no?
The same way I do for the
Yes, sir.
The exact same way. So if I want to find the combined resistance, you all tell me what you think it'd be. Somebody tell me, watch up in your brackets. I just want to see if you'll have the idea.
1 over 50.
Wait, I know it's looking a bit scrappy, so let me just try to make it a little neater. 50 ohms, 7 ohms, 10 ohms, right? Tell me what to put exactly.
1 over 50 plus 1 over 7 plus 1 over 10 to the power negative 1.
Alright, Nikolai, Ryan, be honest with me. Be honest. Did you all know you had to do that?
Yes, sir.
Because I know that you all know how to handle 2, but I didn't know if you all could have handled 3. But anyways, plug that into the calculator and let me know if I get through.
Yeah,
I get 3.8.
I calculate and handle the sheet and then call a fire at one time.
Say that again, Nikolai.
Calculator, call a fire at certain calculator.
No, it will work, don't worry. It will work. You just had up a real brackets. Nikolai, you just had up a million brackets. Alright, so watch. So Nikolai, you gotta plug this into your calculator. Open bracket, then open 1 divided by 50, close bracket, plus open bracket, 1 divided by 7, close bracket, plus open bracket, 1 divided by 10, close bracket, and you're gonna press the -1 thingy that you pressed. And you should get.
But I don't put in already, but it's still call on a half synthetic error.
I feel like you gotta get a different calculator. You can show my picture where you plug in.
They don't show the whole thing, I can show so far.
Show me. Ryan, did you get through or no?
I get 3.8.
Zachary, what had you got? What did you get? Tell me, Zachary.
3.8, sir.
Okay, well, you all got through then. Nice. Zachary, not in here. Well, first of all, Zachary. First of all, Nikolai, I'm not seeing the full brackets.
Well, no, the full bracket, the arrow, the other small arrow, like this, the bracket,
No,
the second bracket.
I not seeing. Okay, for instance, Nikolai, I not seeing. Like, okay, you open a bracket here, but I'm not seeing it closing the bracket for the 1 divided by 50. I just seeing, okay, I seeing 1 divided by 50, but
Oh, hold on. I'm trying to
every time you put in a fraction, you must open the bracket and close the bracket.
Yes, I already think I'll go and buy a calculator because it read off syntax area and then all of a sudden instead of flicker and then call off a number after.
What number you call out?
3.80.
That's the answer, 3.80. Yeah, that's the answer. Say calculator just fine. Right, so Nikolai, we get like exactly 3.80. I round it off.
Nah, exact 3.80.
Right, let me work it out here. So again, Nikolai, you see like how you made a mistake there and you left out the bracket for the 50. You gotta be careful. Anytime you put in a fraction, Nikolai, you need to open the bracket and close the bracket. So let me work it out. So 1 divided by 50, close bracket, plus open bracket, 1 divided by 7, close bracket, plus 1 divided by 10, close bracket to the power -1. Or again 3.8043, and if you round that off, you get 3.80. So RT is equal to 3.80 ohms. So long story short, if I wanted, instead of me drawing 3 resistors in parallel, what could I just draw? What could I draw instead? Somebody tell me. What could I draw instead? Instead of drawing 3 resistors in parallel, what could I draw?
1 resistor in series.
Yeah, 1 resistor in series, and what am I going to put for that resistor?
3.80.
So I hope we understand that. That's how we combine resistors. In the next class, we're going to combine resistors in parallel and series, and then, like I said, I'll introduce V is equal to IR, which is Ohm's law, and we'll deal with those types of questions. But does everybody understand series and parallel circuits up to this point? All right.
Yes, sir.
Well, great. It was a pleasure.
Yes.
It was a pleasure having you guys. Ryan, I'll talk to your dad or your grandma. You tell your dad that you was interested in physics alone, and no maths.
Yeah.
Okay, well I'll just confirm with him. But anyways, guys, hope you have a blessed Saturday. Take care, guys. Later.